one day, and you're thinking about maybe working more that day, or maybe working less, you're going to feel the effect on your leisure supply, on your leisure budget right now, right? You're going to have to work harder today, and you're going to feel the suffering of that today. But the change in income that you get is not going to affect your utility today. It's going to affect your utility over the course of the month as a whole. You're going to spread that out over the month. Okay? So the cost of the leisure that you have to give up, you feel now, but the benefit of the income that you generate is spread out across the month. So if we tried to do our leisure consumption trade-off thing, where we have leisure over here and dollars over here, and just say, well, instead of looking at the month, let's look at the day, it wouldn't work. Because this axis, it would make sense that you would feel this on a daily basis, but this axis, it just wouldn't make sense. Okay? And so we can't, it's like saying, oh, people can't borrow and save from one day to the next. Well, they manifestly have to because they only get paid once a month. Okay, so we need an alternative model. And this is what standard economics has provided us with. Does that make sense, by the way, why we can't use that model? Okay. So here's the second model that standard economics has provided us with for studying labor supply decisions. And this is a model, by the way, that you can use for whatever time horizon you want. It's not restricted to daily labor supply. You could use it for studying a week or a month or a year, whatever you want. But it has the advantage that you can use it for looking at daily labor supply, whereas you can't use the previous one. So instead of thinking of workers as consuming leisure versus money, we're going to think of work, instead of using the consumer choice model and map it onto the labor supply decision, we're going to go and take the model that we used for profit maximizing firms. Okay? And we're going to drag that over and use that to model workers' decisions. So instead of thinking of a worker as someone who's taking a budget of hours and allocating it between leisure and earning money, we're going to think of a worker as a little production plant that is generating labor. Okay? It's using leisure time to generate, well, actually, it generates its output, which is labor, which is like an output good, like a firm that makes widgets. A worker is a firm that produces labor. And then it sells its labor on the output market, and the price it gets for its labor is W. Okay? And so we're going to harness the profit maximizing model and see what happens. Okay? So here's the setup. Let's assume that workers decide each day how much to work that day. And we'll call that L still. And then we're going to give them sort of a quote-unquote revenue function. Now, the reason I'm putting that in quotes is because what we care about isn't actually how much money this person gets, but how much utility they generate for themselves by earning money. But for now, we're going to make that a one-to-one trade-off. So basically, $1 worth 1 euro, whatever that means. Okay? So we're going to treat them just exactly like they were a profit-maximizing firm, just trying to maximize their revenue. And their revenue function is very simple. It's the wage times the number of hours they work. Right? And then if you want to add that up over the month, you could. Their effort cost is going to be some function that, some number of utils. And we're going to assume that the first derivative of that function is positive. That's to say, working more creates a higher effort cost. That's not particularly challenging assumption to make, and that the second derivative is also positive. That there's an increasing marginal cost of labor. That working for the first hour sucks a little bit, but that second hour, adding that second hour, sucks more than the first hour. Okay, and I'll draw an example shortly. I knew this would happen. I knew this would happen. At the beginning of the semester, I found the old-fashioned kind of eraser here, hidden. Oh no, good, I hit it again. You have to hide these because this custodial staff have instructions to remove them because the university has decided that this is a superior eraser. It is not true. This is a superior eraser. So if you see this eraser out, grab it and hide it. I'll give you an example of what I mean from a positive second derivative. It's something like that, right? That's what I'm saying. So it has an increasing marginal effort cost. And then the workers are going to just solve, instead of having some crazy constrained optimization problem, they're just going to have a straight unconstrained profit maximization problem, right? So they're going to choose L to maximize their revenue minus their cost. There's no budget constraint, right? This is like a firm. Firms don't have a budget constraint. As always, when we're doing optimization using calculus, we take the first order condition, which is we just take the first derivative of this optimization of this objective function, set it equal to 0. And we just get, right, the first derivative of that is W minus the first derivative of the cost function, which we'll just call marginal cost for now. Okay? Yeah. Sorry? Oh, yeah. Okay, yeah. So you would like this to be subject to the constraint that L has to be less than or equal to H. That's fine. It won't change the results. Yeah, that's totally fine. We don't actually. So so that kind of boundary constraint, usually the way you deal with that is solve the problem and then just make sure that you didn't go over the boundary. You don't actually have to mathematically include that. You don't have to write out a Lagrangian. Just check and make sure that your optimizing labor supply isn't like 45 hours a day. And then if it is, you say, oh no, that's a corner solution. We'll just make it 8. But that's not going to come up. I don't know what we're going to do here or what we're going to do in the problem set. I promise I won't make you worry about that. But thank you for pointing that out. There is a sort of a boundary constraint there. But the basic optimization rule, provided that you don't wind up working more than 24 hours in a day, is that the first derivative of this thing better be equal to 0, and that implies that you will work until your marginal cost of an additional hour of work is equal to the marginal revenue you generate from doing so. Right? That's a standard. Remember P equals MC, profit maximizing condition for a firm. Same exact thing, right? Okay. And this is, just so we're clear on what's going on, the marginal cost is a function of labor. The more hours you put in, the higher your marginal cost gets. Right? You've worked a 10-hour day. That 11th hour is really going to cost you a lot extra. So you're going to say, why? Is that really worth another hour's worth of wages? Maybe not. Okay. So that's how that model works. And I'll give you. We'll put a function in there in a second and see what actually happens. Okay. Indeed. Let's do that right now. So I guess I'll just do this on the screen. I may regret it. All right, let's do this. We'll have L over here, right? This is sort of inputs versus output. So how much labor, how many hours are you going to put into generating revenue for yourself? And then on this axis, we're going to map both the revenue that you earn and also the cost, the effort cost that you have to put out. So the revenue will just be WL, okay, which is some straight line like that. And then we'll sort of say, all right, let's have the cost function just be L squared. This is often mathematically the simplest thing. If you just really want to just cut straight to the intuition and not worry at all about any complications, just go with the right-hand side of a parabola, L squared. And what that means is that this so-called revenue function, if you want, is WL minus L squared. Well, WL is the height of that line. L squared is the height of that parabola. If you subtract one from the other, literally what you get is the difference between the two, right? That distance right there is your revenue. So what we want to know is, where's that distance between the two lines maximized? Sorry, that's not your revenue. That's your profit. That's your didn't mean revenue, I meant profit. That's your quote-unquote profit, right? It's just the difference between how much you brought in and how much you had to put out. And we want to know where that little line segment is biggest. It's biggest where the slope of this curve is the same as the slope of that line. Okay? So let's say that that point of tangency is like there. That's going to be the place where that line segment is the longest. That's what that profit maximization rule, that's what W equals MC means. It means that the slope of that cost function is the same as the slope of the revenue function, which means that the difference between the two, which is your profit, is maximized. Yes, Alice? Oh, goodness gracious. Yeah. Thank you. Okay, so you'll find a place where those two slopes are equal, and that will be your sort of quote-unquote profit maximizing or utility maximizing labor supply. Okay. I see I've broken the cardinal rule, and I'm going to now get... Oh, that's great. I actually have the axes on my screen. Oh, boy. And then, okay, this is annoying. Has everybody got that written down? Okay. I'm going to get rid of it. Go on. Go away. We don't want you anymore. Okay. Here we go. So what we had was we had that, and we had that. And we had some point of tangency, and that defined labor supply. Okay. If the daily wage is constant, then the number of hours you work is going to be constant, right? Nothing changes, nothing changes. We call this effort smoothing, and it makes sense. You wouldn't want to say, oh, well, you know, if I've got 5 days a week and the wage is going to be the same every day, let me get all of my work out of the way on Monday and Tuesday. Let me just work 14 hours those 2 days, or 15 hours, or whatever, and then not work the rest of the time. Because on those 2 days, you would be pushing yourself up into really, really high effort cost, right? The marginal cost of those, that 13, 14, 15 hour would just be killing you. So you want to smooth out your effort over the days because of the convexity of that curve, of that effort function, that effort cost function. Okay? So convexity will get you this kind of smoothing in all kinds of models. And so the prediction here is that you'll want to work the same number of hours each day as long as the wage stays the same. The thing we actually care about here is what will happen when you have transitory wage changes. Okay? If there's a wage increase on a given day, let's say that you know in advance that on Wednesday your wage is going to be double what it is on the rest of the days of the week, this model predicts that on Wednesday you should work more, and the other days of the week you should work the same as you always do. So you should take advantage of the fact that there's a higher wage, because then that 9th, 10th, 11th hour suddenly is worth it on that day. Right? You're just trying to maximize the total amount of income you make in a month, so you're going to follow that same maximization rule every day. And you can see this. If we crank this line up, right, if this here is W times L, and this is some W prime times L, now why have I got this? What? This is now wrong. No, it's not. I just need to extend it. Whoop. The place where these two lines are parallel to one another is now going to be way over here. Okay? So that's going to be L star prime. You're going to work more because now there are more hours of work for which the wage is greater than the marginal cost. Does that make sense graphically what I did? Crank up the slope of that revenue line, and the point of tangency gets pushed out to a steeper part of the effort cost function. Yeah? So you should work longer on days with higher wages and less on days with lower wages. And even if you believe that people are just shooting to make the same amount of money every month, you should still work more on days with high wages and less on days with low wages. This is a completely unambiguous prediction of this model. Right? There's no daily income effects here that would make you want to work less on a day with a higher wage. There's nothing in this model that would ever suggest that people's daily labor supply would be downward sloping, that they would have a negative elasticity of daily labor supply with respect to transitory wage changes. There's nothing in this model that would get you that. Okay. Okay. Just to make sure that you're absolutely convinced. Suppose that we have this WL minus L squared, which means that the first order condition, right, if we're maximizing that with respect to labor, the first order condition is just that W equals 2L, which implies that the profit maximizing or utility maximizing supply of labor is just half the wage. Okay. Okay, let's suppose that we have a 2-day month. Just to keep it, just a really, really simple two-period model where there's 2 days in a month, and you're trying to maximize your total profit. So let's just suppose that the wage on the first day is equal to 14, the wage on the second day is equal to 18. Okay, so what this says then is that on the first day, the profit maximizing number of hours is 7, and on the second day, the profit maximizing number of hours is 9. Okay, let's see what happens if you violate your profit maximization rule and just work the same number of hours. Okay, let's suppose that you come along and you say, no, I'm going to work 8 hours each day. Okay, so if we have L1 equals L2 equals 8, what we're going to get is that your earnings, so your revenue, is going to be 14 times 8 plus 18 times 8, which is equal to 112 plus 144, which is equal to 256. Sorry, I know this is agonizing, but I also know that if I don't do this from time to time, people will say in my student evaluations, it would have been nice if you'd done more numerical examples. So here we are. Meanwhile, the cost, right, is going to be 2 times 8 squared, right? Because on both days, you're just plugging that same 8 into the cost function. That's 2 times 64, which equals 128. Whoops, 128, which means that your profit, which I'll just call pi, is equal to 128. Yeah? Straightforward. If instead you had done what the model says you should have done, then you would have had revenue of 14 times 7 plus 18 times 9, which is equal to 98 less on the first day and plus 162, quite a lot more on the second day, and that equals 260. And your cost would have been 7 squared plus 9 squared, which is equal to, looks like I didn't write out the two parts, it's 130. So in this case, your profit is 130. Now, it doesn't look like you gained much, but remember, those are utils. And they could be huge, you just don't know. Could be really, that 2 util increase could actually represent quite a lot of benefit. The point is that by following the rule, look what happened. Your effort cost was more. Your effort cost over the week, you worked harder. Same total number of hours, right? 7 plus 8, 9 is the same as 8 plus 8. But because you didn't smooth things out, sure enough, you paid an extra effort cost because on the second day you pushed yourself into really high marginal cost. But look what you got out of it, right? The benefit that you got, the increase in benefit from 256 to 260 was greater than the increase in cost. Okay, so you don't want to smooth effort here. You want to smooth the actual net earnings. Or not, sorry, not smooth the net earnings. You want to maximize the net earnings. Okay? Not surprisingly, it's not what we actually observe. By now, this is going to be like a sitcom. You'll be able to predict the plot very easily, right? I've shown you a standard model. I've shown you a completely unambiguous prediction of the model. And it's like Scooby-Doo, where at the end of every episode, they pull a mask off some monster, and you see that it's the guy that runs the amusement park. Okay, so now we're going to see evidence of an anomaly. It's not actually the case that when people have a transitory wage increase, they unambiguously work more on a daily basis. Hold that thought. Pal said it's not just because they don't know better. It may be because they don't know better. But remember the billiard analogy? The point that Friedman made, that quote that I gave you on the first day of class, is that we're not actually suggesting people know why they make the decisions they make. We believe, when we use these models and say this is a good enough approximation, it means we believe that regardless of how they make their decisions, their choices will wind up fitting this model. Whether or not people know better is actually a very interesting question, because a lot of times these models, right, if you think about, here's where we started you. Economists love to do this. We'll start you with something that's so intuitively obvious you can't argue with it. Then we'll change it without telling you. Okay? If this is apples, and this is bananas, and I'm going to model your choices as being determined by some indifference curve that I got from some map of indifference curves that I could rationalize with a utility function and find a point of intersection with some budget constraint, right? It doesn't matter to me that you don't pay attention to the prices when you go into the store every time. It doesn't matter to me that you couldn't tell me what the shape of that curve is. It's so intuitively clear and straightforward to say people prefer a balanced bundle of apples and bananas rather than all apples and all bananas. And that they can rank that people have been eating apples and bananas all their lives. They know they have complete references. It's so intuitively clear. Because you don't have to do any math here. If the price goes up and you didn't notice, you're going to notice at the end of the month. Because all of a sudden you can't make rent. And you're going to go back and look at your receipts and say, whoa, the price of bananas went up. Next month I'm going to eat less bananas, right? This doesn't actually place any kind of cognitive or computational burden on the individual whatsoever. And so the billiards analogy makes a lot of sense. Because you don't actually need to know any laws. You don't have to be an expert at buying apples and bananas to get for this model to fit. Right? A totally uneducated consumer of apples and bananas is likely to behave according to this model. Now, when we start getting into how to maximize your income when you have transitory wage changes, we start adding like maybe you actually have to be a little bit on the smart side to figure out that you should be working more when the wage goes up. And so maybe it actually does matter whether or not that billiard player actually knows the laws of physics. Maybe it actually does matter whether people actually do the math. Maybe it does matter whether or not the taxes, for example, just a random example, are included on the price tag or not. Because maybe people don't take the time to multiply the price by 1.09265 or whatever, 9875, and realize that they should actually be, yeah? So we start getting into this question of whether or not people actually do the math. Hold that thought. If we get to the end of the lecture, it'll come back around. But first let me convince you that, that the prediction of the model is not correct. Okay. So we need in order to be able to observe this, in the real world, we need a situation in which workers actually get to choose their own hours every day, and that their wages fluctuate daily in a way that they're used to. Okay? There aren't very many examples. My wage fluctuates once every 2 to 3 years if I'm lucky. Okay, Kammer, Babcock, Lowenstein, and Thaler, 1997, very famous paper. I still don't know who Babcock is. Kammer, Lowenstein, and Thaler are, let's say they're unarguably in the top 10 behavioral economists in the history of the field. And we'll meet them again repeatedly. Well, we've met Thaler already, right, because we read Kammer, Connection, Thaler. Okay, so they found a labor market that satisfies our needs, which is the New York City cab driver market. Okay, so cab drivers, as it turns out, typically the way this works is that you lease a cab, maybe you even own it, but if you lease it, you pay for a shift, you pay a fixed fee for a 12-hour shift, but you don't have to work that 12 hours, you don't even have to take the car out. Right, because the person who's leasing you the car, all they're going to get is the fixed fee, they don't care if you make any money or not. As long as you don't trash the car. So how long they actually work in that 12-hour period is up to them. And then it turns out that their effective hourly wage, they're not paid a wage, right? They're paid the fare that they get from the people who ride. But how much they can effectively earn in an hour varies according to factors that are random, at least to them. They're not really random. They're things like, on a really rainy day, more people are going to want to hop a cab, right? Or if the subway breaks down, more people are going to want to hop a cab. If there's a big business conference, there's going to be a ton of people needing cabs in a certain part of town. And all of that makes it possible to earn more money per hour. Okay, so their effective wage fluctuates in a way that is random, but known. They're familiar with the random distribution of these wages. So if the wage is high one day, they don't suddenly think, ooh, I suddenly have a permanent increase in my effective wage. They think, oh, it's a high wage day. Okay? So these guys, what they did was they went down and actually collected from a few different cab fleets the trip sheets that these drivers fill in, where they write down how much they worked that day and how much they earned. Okay, and then you can compute from that, if you know how many hours they worked and how much they earned, then you can compute their effective hourly wage, right? So their wage is just computed by dividing their earnings by their hours. What you're doing now, this is just an econometric note. So this is just a methodological note that I want to make because it's a really important thing you got to understand about this paper, and because it'll help you when you get to 140, or it'll make sense to you if you've taken 140 already. If you're trying to study the relationship between hours and wages, where wages is represented by or is computed as earnings divided by hours, suppose that there is measurement error. People are writing down their hours on this trip sheet, but they're getting it wrong a little bit. Sometimes they write down a number that's a little too high, sometimes a number that's a little too low, because they're not being precise. Yes? That's reasonable? What that means is that if they have measurement error that makes the number they wrote down for hours high, it is mechanically going to make the number you compute for wages low. So if you then look at the relationship between hours and wages, it's going to be negative by